today I just want to go over some very basic and extremely beautiful, I think, combinatorics of symmetric groups, partitions, etc. So the goal of today, so we spent 2 weeks on a Kuhn-Koch-Werschig, and I hope that now people have some picture of the symmetric group, representation of the symmetric group of characteristic zero, which is basically like there's some kind of reasonably complete, solid theory there. And now we ask ourselves what happens when we reduce mod P. And I think what I was trying to emphasize 2 weeks ago is that in order to do something much harder, which is the mod P theory, we should understand the characteristic zero theory really well. And that's in some sense what a Kuhn-Koch-Werschig somehow instigated, and then there were some follow-up works. And so now I just want to explain a little bit more of the combinatorics of symmetric groups and explain the connection to affine Lie algebras, which is, I think, totally amazing. So I kind of hope that many of you went to Alistair's IFS. So we have sim, which is the ring of symmetric functions, which has the inverse limit over symmetric functions in variables. So we think about a symmetric function as basically being in infinitely many variables, but whenever we compute infinitely many variables. And inside here we have Hn complete symmetric functions. We have En elementary. And we also have S lambda for sure functions. So for example, H2 is x1 squared plus x1 x2 plus x1 x3 plus x1 x4 plus x2 squared plus x2 x3 plus off to infinity. E2 is x1 x2 plus x1 x3 plus x1 x4 plus x2 x3 plus off to infinity. And Schur functions, so these are parameterized by positive integers, and the fundamental theorem of symmetric functions tells us that these are multiplicative basis. So symmetric functions are a polynomial ring in these ones and these ones. And these Schur functions, these are parameterized by partitions. Partition. And this is a Z basis. Okay. And we define sim which has a fancy S to be the direct sum of all the representations over C of symmetric groups. And as Alex pointed out many moons ago, it's very important to start at 0. And this is a monoidal, so if I take two representations of symmetric groups, I can tensor them together. That's one monoidal structure on one of these, but the whole lot of them together gets a different monoidal structure where I define M tensor tilde N to be the following. First, I take the external tensor product of M and N. So this is a module over Sn times Sn. So let's say this is a representation of Sn, and this is a representation of S. Whoops.
The other way around?
The way around. N and N. I take their external tensor product. So this is a representation of Sn times Sm. I include that as a Young subgroup inside Sn plus M, and I reduce. And, you know, if I do this 3 copies, that's the same thing as just taking a 3-box product and inducing up. So this is the associative word order structure. It is also commutative because Sn and Sm are conjugate inside Sn plus M. And this induces a ring structure on the Grothendieck group of sim C, which is the direct sum of the Grothendieck groups of sim of rep. Yeah. Okay, so this means growth and decrease. I hope now everyone is happy with growth and decrease. Please tell me if you are not. And I have a convention which is maybe somewhat unusual, which is whenever I write square brackets for an abelian category, it means abelian growth and decrease. Whenever I write it for an additive category, it means additive growth and decrease. So I just want to do a brief aside. Everybody happy with that? No lecture next week, that's the most important thing. And the lecture after that, that's also important. Okay, so I'm not sure how many people have done kind of symmetric functions, but so this is important. If I take H1 times S lambda, beautiful formula, the sum overall lambda goes to mu by adding a box of S mu. And Hn times S lambda is the sum overall lambda goes to mu by adding n boxes, none in same column. And the beautiful rules. And you know, this is exactly the same as our rule from the symmetric groups for induction from Sn to Sn plus 1. Very nice. And so I don't know, it's incredibly beautiful that these like combinatorial rules come out of this, what looks like, you know, pure algebra. Okay, and so theorem, I'm scared to run on this board because it's basically unerasable, but anyway. So we know both what sides very well. And so we have the following beautiful theorem, which is that S lambda goes to the class of M lambda. So this is the, I'm not really sure how to write the simple Sn module given by a partition lambda, but anyway, I'm writing it M lambda. Is that criminal, Andrew? What should I call it? What do you call it? D lambda, that's right. But yeah, characteristic zero. Not S. S lambda. Okay, big S, that's great, because that's, yeah. So this means this is categorically fantastic. So this is the irreducible irreducible parameterized by lambda.
So the irreducible of Sm?
Of Sn.
I think you use B lambda at previous sections.
Apologies. I'll use that lambda now.
It won't be confusing with Sn.
Maybe. Yeah, you're right. Thank you. So this is a map, and it gives an isomorphism of rings between sim is isomorphic to the growth and decrease of sim. Okay, so that's extremely beautiful. And so, for example, HM goes to triv M. So this is the trivial representation of the M symmetric group. EM goes to the sign representation of the M symmetric group. Yeah, I didn't say monomial symmetric function, but so if you like these things, monomial symmetric function goes to induction from Williamson. You can ignore this if it doesn't make any sense.
So who proved this first, actually? It seems
No,
to be like a folk result somewhat.
yeah, no idea.
And somehow, like, in order to understand this, you need Schur-Bell duality, right? In order to actually, like, understand this isomorphism, or...
It depends what you mean by understand.
I mean, like, you would not be able to cook this up unless you use Schur-Bell duality, like, or maybe not. How else would you,
I mean, I think that I claim that, like, already just knowing this, you have a proof.
No, yeah, I'm not saying a proof. I'm saying, like,
okay.
where the heck would you cook this up from? Is there any other way to see this besides Schur-Bell duality?
So there is another way,
Okay.
which is, so this is this other approach. You know, when I started off the symmetric group lectures, I said that there's like 4 main approaches to representation theory in symmetric group. So the one that I didn't talk about is this circle of ideas, which somehow I associate with Zelevinsky and Bernstein, which is you build this big Hopf algebra,
Okay.
and then you say by theorems of Hopf algebra.
Okay. You just proved that the growth and decay has the structure of a positively symmetric graded Hopf algebra with a binary form, and then there has to be that.
Yes, exactly.
Right.
And somehow, like, I think that Zelevinsky definitely explains that all of the combinatorics of, like, you know, you can get all of the characteristic zero combinatorics of symmetric groups out of that approach.
Yeah.
So that's another approach. But definitely what Alex is saying is correct in that, you know, like when I look at this, I see a symmetric power a symmetric power representation of a general linear group. Yeah. And here I see an exterior power, and I'm thinking about Schur-Bell duality secretly.
But wasn't Joe a student of Frobenius? Like, didn't Frobenius cook up? Didn't he do this with, like, generating functions and, like, heaps and heaps of polynomials before Schur-Bell duality was a thing?
Correct. And then he said to Schur, you should use this to get the representations of the general linear group.
Oh, okay.
Yeah. So historically, symmetric groups came first.
Okay.
I'm really trying to get to the end of the lecture today, so I'm going to try and bridge these slides a little bit. So remark, which doesn't mean I don't like discussion, but it just means that I need to be somewhat sparing in what I write on the board. So HM, so multiplication by HM corresponds to, under this, corresponds to the direct sum of induction from Sn times Sn to Sn plus m of blah tensor through m. So that's just tautological from what. So multiplication by HM corresponds to this function, which I want to call H. And in particular, H1, which is this innocent little operator, this is just x1 plus x2 plus the symmetric function x1 plus x2 plus very innocent guy. This corresponds to induction from Sn to Sn plus 1. And here I should put Sn times S1 and then put trivial representation of S1. But there is only one representation of S1, and it is the trivial representation. So this is blah. So it's just this. So that's what I call H1.
And you're direct summing over that.
Direct summing overall. Yeah.
Like now we're thinking of this as a big, like the direct sum of all the representation categories. So we've got these functions going up and down.
Yeah. So I just want to point out that this is a very innocent little dude. You know, just induction from Sn up to Sn plus 1. But we get an enormous amount of mileage out of it in a good compound sheet. And then almost you get everything, and then you've got to look at one other innocent dude, which is the analog of H2, and then you can already get everything. Just, I think, really striking. So we get a hell of a lot of mileage out of this one functor, H1, which from a symmetric function point of view is almost trivial. Okay. Save that remark in your head, please. So now, again, I'm avoiding writing everything that's in the notes, so if you're stuck, please look at the notes, but remember the following. symmetric functions has this bilinear form, which is the sure functions are a self-dual basis. S lambda S mu is delta lambda mu. This bilinear form is the decategorification of the Hom form on these symmetric groups. Yeah. S lambdas correspond to irreducible representations. Sure's lemma tells me that if I Hom V lambda to V mu, I get 0 unless lambda is mu, and if lambda is mu, I get a one-dimensional space. Yeah. So this is the statement that this form so this is the form on sim corresponds to Hom on sim. So in particular, adjoints in the sense of linear algebra correspond to adjoints in the sense of category theory. So in the sense of linear algebra corresponds to adjoints in this category theory. So if you remember Alice's IFS talk, and a very important role was played by HM star, the adjoint of HM under this form. And HM star corresponds to the adjoint of this, which is the direct sum, restriction from Sn plus m down to Sn, and then I take Sm invariance in fact. That's the adjoint of that. And H1 star corresponds to the direct sum of the restriction from Sn plus 1 down to Sn. So, I'm hoping you were in Alistair's talk. I did bang on about how people should go to Alistair's talk, so I feel like I'm not being
What's the SM up in the top, right? Or the monogram?
what's that?
Yeah.
SM invariance.
Oh,
So I take, essentially, sorry, maybe I should write it down like this. I take a modulo over Sn plus m, I restrict it down to Sn times Sm, and then I take invariance under distance, which is adjoint to tensoring the distance. Now, let's say that, yeah, so basically you have this extremely important algebra called Heisenberg algebra, which is defined to be the subalgebra generated by H1 multiplication by HM and its adjoint. Yeah, so this means generated now. Yeah, this is generated by, and not overall n negative equals 0 inside endomorphisms of okay, so that's the definition of the Heisenberg algebra. But now it's like just patently obvious how we categorify this. We define highs. You know, in this talk, my method of categorification is I just write a blackboard poll. Magic. Is generated by HM and HM star overall n equals 0 inside endofunctors of sim. Okay. And I really want to emphasize that as something very important, because just, you know, some people in the audience have seen some higher representation theory, but this is really a kind of revolutionary new thing to do that we've started doing probably, you know, maybe some people like Grinfeld or something knew to do this in the 70s, but it took many people a long time to catch up with Grinfeld. And people really started doing this in, I guess, the late 90s and early 2000s, which is you start, so if you think about classical representation theory, you think there's a vector space, I would like to understand it. So for example, the space of functions on a circle, I would like to understand this. And then you invent, you look at the rotation action and you invent Fourier series, for example. Or there's a space of functions on some manifold, etc. And you do representation theory. The revolutionary thing here is to say, here's a category. I want to understand this category. And I do that by understanding symmetries of this category, i.e. interesting endofunctors on this category. And it's remarkably powerful technique. So there's categorification, all this kind of world. And I just want to emphasize that this is very complicated thing, but somehow we end up understanding it just studying this endofunctor H1 and maybe H2. So the very simple algebra of endofunctors and has very rich structure that allows us to understand this category.
So when you had that theorem, you had a theorem, but the theorem was in terms of the growth of degree. And then everything on this point, you've forgotten about the growth of degree. And you're just working in the category.
Exactly. Yeah, exactly.
But why are you doing that?
So, yeah, so what's the best way to explain this? So this is a statement about
the goal. Like the goal is to understand the non-sim C, is that right?
Yeah, so maybe the point of view is the following. We can be old school Frobenius and be very good at manipulating all these symmetric functions, etc., and be very clever and finally deduce this theorem. Or we can, 100 years later, literally 100 years later, start applying a slightly different point of view on things. So Frobenius was the first person that said it's powerful to linearize a group action. And now we're taking the next step, which is to say, in order to understand a category, I'm going to understand endofunctors of that category. So the old school representation theory is I want to understand a vector space through some interesting endomorphisms acting on that vector space. Now we're saying I want to understand a category through some interesting endofunctors acting on the category.
So hides is itself the category, or blackboard hides is a category.
Yeah, so this is a monoidal category. Yeah, it's a subcategory of endofunctors of category. So it's a monoidal category.
So the objects are functors, morphisms and natural transformations, and the monoidal structure is composition.
Absolutely correct.
Yeah. So is part of the point that when you're working in a categorical setting, now you on the level of the growth in your group you need all of the HIs, but in the categorical setting you only need capital H1 and capital H2 because now you have the endomorphisms of these functors, and that has a lot of extra data, and then you can study things that way.
Yeah.
Okay.
And it's unbelievable, one of the things that happens in Triangle, which I'll hope to explain at the end, well, I'll explain next week actually, is that you just check, you have this functor, you have an endomorphism of this functor, and then you have an endomorphism of its square, and somehow this structure is so generative. It's really remarkable. And maybe, so the rave that I wanted to say is that I think that it's interesting because representation theory started because, representation theory didn't start because representation theorists wanted to classify the representations of a group. Representation theory started because it was useful understanding all this stuff, understanding quantum mechanics, understanding the standard model, trying to understand how tensors move in general relativity, etc. So representation theory started because of the broader scale of maths. And I feel like in higher representation theory, representation theorists have discovered something absolutely amazing, but somehow we're using it on representation theory. And it hasn't yet really been used out in the wider mathematical universe. Because it is pretty complicated, but it's also incredibly powerful.
Oh, in low-dimensional topology.
Yeah, that's true. In low-dimensional topology and a little bit in kind of Langlandsy type stuff, but yeah, it's yet to filter out.
But honestly, representation theory also took a while to get really started, right?
Yeah, absolutely. Yeah, it's a very non-obvious, and that's what I think it's really important to remember. You had amazing people studying finite groups, and nobody like took representation seriously for 60 or 70 years. So like it's not obvious to study representation theory, and it's not obvious to study higher representation.
That's right.
But it's useful.
Maybe just a plausibility argument why you might want to do this if you were just hardcore, all you care about is smaller things. Like part of the problem is if you say induce a representation and you want to decompose it, or you want to get an EREP out of it, you need to decompose it. But if all you've got is growth and decroups, you can't really do that. But as soon as you've got a functor, it's already decomposed, so it turns into a different problem of like, can I recognize these indecomposed pieces in a different way? So that's exactly what we did in the symmetric groups case, where we looked at the endomorphisms of this H1, and that gives you your pieces, and they're all one-dimensional.
Yeah. I hope that what Chris just said made sense. So just a remark. So sim is a simple eyes module. Oops. And sim is a simple eyes module. And I just find that like that statement by itself is already mind-blowing. And it's just basic, like if you think about a simple module, you don't need to understand very much to nail it down in time. And here I'm saying that the direct sum of representations of all symmetric groups is a simple module over some whatever.
Are we still in characteristic 0?
In characteristic 0, yeah. But yeah, I think and also you can say, Geordie, what do you mean by a simple module over simple category over one other category? Yeah? And that's a subtle question, but maybe we can. It's good to think about before you say what is that. So now exactly what Chris was saying. On a growth and D group, I take a module, I take a class of a module, I induce it up, and I've just got that. I've just got a vector in some space. Can't do anything. But if I have a simple module, I induce it up, and I have an interesting algebra of endomorphisms, then I can start breaking that thing up. That's where the power of these extra endomorphisms come from. So the really important thing is, if you have a monoidal category, you have to start asking, what are the morphisms between monoids? Very basic question. So, example, let's consider restriction from Sn plus 1 down to Sn. And I would like to know what are the endomorphisms of this functor. So this is a functor. So this thing is an algebra. Now, we haven't been over this yet, so I just want to say it once because it's very important, which is that functors are often bimodules, and bimodules are usually easier to work with than functors. So an example is that restriction from Sn plus 1 down to Sn is isomorphic as a functor to tensoring with this bimodule B, where B is the bimodule Csn plus 1, viewed as a Csn plus 1 Csn bimodule. So this is a in a category of bimodules over Csn plus 1. Okay. And what I'm saying here is just totally tautological, but it's still useful. So yeah, it's totally tautological that this functor is this, because what I'm just saying is I'm kind of saying take my representation and forget that. So for example, if I just took the bimodule Csn plus 1 as a bimodule over itself, and that would be the identity functor. And now I'm just saying take this thing and restrict the identity functor on the left. But now the reason that bimodules are so useful is that Hom, you can work out Hom as functors from Rsn plus 1 Sn, Rsn plus 1 Sn is the same thing as Hom bimodules from B.
Okay, just a silly question. When you write the restriction, this is a direct sum of all n.
Oh no, now I'm just working in a given Sn. This is a functor from Sn plus 1 to Sn modules. And in a second we'll go back and say, I just want to understand this functor. I want to understand all the pieces of this functor. So this general blah 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 is that if I have a functor, it's a difficult question whether or not it's given by a bimodule. Like there's various theorems that say sometimes it is, sometimes it isn't. But if you know it's given by, if you have two functors which you know are given by bimodules, then homomorphisms of functors are also always morphisms of bimodules. So once you've nailed down a bimodule, you're happy. And so the lemma, which I think is again very beautiful, is that, let's say, lemma over here, is that this thing is exactly the centralizer that was coming up. So this is all the things inside Sn plus 1 that commute with multiplication on the left and right by Sn. So before we were saying this controls branching. We were saying that if this is commutative, then branching is multiplicity 1. And this somehow is giving a deeper reason for why this thing shows up. It's the endomorphisms of the functor of restriction. So I want to prove this lemma just because it just illustrates kind of how to work with bimodules. So proof. So if I take phi inside Hom of bimodules from Csn plus 1 to Csn plus 1. This is determined by, so this is a right, in particular it's a right Csn plus 1 morphism, so it's determined by where it sends 1. Determined by phi 1. And now let's see when this is so when is phi a Vim endomorphism? So we want that A phi of x, we want that phi of A dot x dot B is equal to something phi of A dot phi of x dot B. And now, how do we work this out? So this is phi of 1 dot A dot xb. So this is equal to AXB, and then the way that I work out my Hom from phi of 1 is I just write multiply by AXB. So this is phi of 1 times AXB. And this is A times phi of 1 dot xb. Okay. So this is equal, if and only if A dot phi of 1 equals phi of 1 dot A, or A, i.e. if phi of 1 is in the central line. This comes to an elementary computation, but also I think it shows you, if you haven't seen this before, it's pretty amazing. Like if you told me, can you work out the endomorphisms of this functor? And I didn't know this trick, I'd run for the hills. You have to somehow produce some map between, so what does that mean? It means whenever I have an Sn plus 1 module, I have to produce a canonical map from the functor applied to that module to itself that's natural, that commutes with everything. I run for these. But once I've worked out it's a bimodule, then I just look at what are the bimodule homomorphisms, and in 2 lines basically get the answer. It's very useful.
Is it possible to say that if you give me an element in that center, what the endomorphism is?
Good question. Maybe I erase this board and you answer when I finish erasing the board.
I would say yes. And another way to see this is that the endomorphisms of a functor looks like it's heaps of data, but sometimes in your category it's not heaps of data, because endomorphisms of a functor induce endomorphisms of every object. Like you apply that functor to an object. So you can find an object which hits has a map to any other object, sort of naturality of your of the endomorphism tells you that it's sort of determined by what it does on a single object. So in this case, we're looking at what it does on the regular SN representation. And we see that, well, we need a map from the regular SN n+1 representation to itself over S little n. And that gives us our centralizer. So like, and that's also how you can show things with bimodules. If you have like one thing which sort of generates your category.
And you would also see that this is also the endomorphisms of induction. By exactly the same, the bimodule is just it's swapped the other way around. Great. And so what that tells us is that restriction. Sorry. Remember that H1 was this direct sum of all the inductions from Sn to Sn plus 1. H1 star is the direct sum of restriction from Sn plus 1 to Sn. And now this discussion tells us that these both have an endomorphism X, which is the direct sum of the Juices-Murphy element on plus 1, where Jm n plus 1 is 1 n plus 1. So we've been having a lot of fun with this element in the last n plus 1. So this lies in the section. So this thing is fixed under conjugation by Sn, which moves these position, the first position around. So this dude acts as an endomorphism of restriction from Sn plus 1 to Sn and induction from Sn to Sn plus 1. So I take the direct sum of these and I get an endomorphism of this functor and this functor called X. And so now we can break up H1 and H1 star into eigenspaces. We can break up H1 A. Also, we know that took a bit of work, but we deduced at some point that all the eigenvalues of this Juices-Murphy elements are integers, and they're given by the contents of the corresponding partition. And so all these, so we get these decompositions, H1 star, X element, F alpha, and Z, into generalized. Okay, so at this point, we don't need generalized. We don't need yet. We saw that these generate semi-simple algebra and the Juices-Murphy elements are semi-simple, like semi-simply on any module. So we could just say eigenspaces in them at the moment. But when we go to characteristic P, we need to say generalized.
So the left-hand side is a functor.
The left-hand side is a functor. Yeah. And I can break a functor up into eigenspaces if I have a functorial endomorphism of that functor. So let's say I have a functor that takes something and spits out a vector space. So this is just something, takes something, spits out, I get a vector space. Imagine if this functor has an endomorphism. What that tells me is that that vector space has an endomorphism. And now I can decompose that vector space into eigenspaces of that endomorphism. And the fact that this is an endomorphism of functors tells me that this decomposition into eigenspaces will be functoid. So if I want to apply EA to some representation, I apply my functor, I split it up into eigenspaces under X, and then I take the 8th eigenspace, and that's the value of, so.
But don't you have one eigenvalue for every of these juices Mercy elements?
Yeah, but I'm
one.
So I take this n plus 1 means this only, like when I apply this to an SN module, I only apply the n plus first juices moving on. So EA of V is the A eigenspace of X V acting on H1. So this is a machine that whenever I put in a representation, I get a morphism, A eigenspace. Okay, and now we have these beautiful. So
I don't understand that clarifying remark. What is XV?
So XV is an endomorphism of, so, XV is an endomorphism of the functor H1.
Oh, okay, sorry. Yeah, good.
Yeah, maybe that was a de-clarifying remark.
I'm re-clarifying. Good.
Right. So we have that E alpha. So EA of M lambda is direct sum overall. Lambda goes to mu by adding a box of content A. Oh, sorry, I keep reading V lambda V. Okay, so if I plug the simple V lambda, I get this direct sum, but notice that this is either 0 or irreducible. Okay, if I give you a partition, EA would be like if I want to apply E7, so there's some diagonal. This is my content 7 diagonal.